Okay, there really is a lot of material to cover for module 6, no? And I don't want to rush things, no? So I decided to slow down, basically to slow down. And then this is what I'm going to do. We're supposed to finish module 6 next week, but actually the end of the semester is still going to be, I think, the week after, no? So if I'm not able to cover everything that I think is important for module 6, then I'm just going to extend to the week after next, no? If you're available, you can attend. If you're not available, it's okay with me. So ganun na lang yung gagawin ko, ano? Okay, just to go back to our discussion the last time. Okay, we said that this is the generalized form of a gain expression. Later on, we're going to have some exercises where you're going to get the gain expressions of amplifier circuits based on the small signal model. Okay. And then we said that, okay, this is the generalized form. Okay. You can manipulate this into this. How do you do that? First of all, you factor out a sub n from the denominator. Then you factor out b sub d from the denominator. And then you get the roots of from the factor out a sub n from the numerator. Then you factor out b sub d from the denominator, no? And then you get the roots. You get the roots of the remaining polynomial in the numerator. You get the roots of the remaining polynomial in the denominator, and you're going to come up with this expression for your transfer function a sub s, where the z's are your zeros and the p's are your poles. Then we said that poles and zeros can either be real or complex. For the meantime, we will just consider real poles. Now, if we're interested in the frequency response, then you replace S with j omega. And if you recall, when you do this, you're actually, pag tinignan nyo yung surface plot, I showed you the surface plot last time, you're actually getting a cross-section of that surface plot in the S equal to 0 plane. That's what you're doing. Okay. So we replace S with j omega. So we come up now with an expression for our transfer function in terms of j omega, and then we can manipulate that so that it will be of this form. So you have to do again some manipulation. Okay. Now, what is this form now? You have zero terms in the numerator, and you have pole terms in the denominator. And then omegas of Z1, omegas of Z2, omega all the way to omegas of Zn, those are called your zero frequencies. And then omegas of P1, omegas of P2, until omegas of PD, those are called your pole frequencies. So you're going to have zero frequencies and you're going to have pole frequencies. Okay. Now we can treat your zero terms and your pole terms separately. And the reason why you can do that is later on you're going to see, because we're working in the log domain, all you have to do is add up the responses of the different terms that are treated separately. No? It's, in some way, it's like superposition. Okay, I'll skip this, no, because we went through this already. So how do you treat your zero terms? So this is a generalized zero term. Okay, 1 plus j omega over omegas of O. Your magnitude is the blue curve, but if we're dealing with Bode plots, then we use the red curve to approximate the blue curve. So yung magnitude nito, that's the blue curve. But we're doing Bode plots, so we use the red curve to approximate the blue curve. Your 3 dB frequency or your half power point is at omegas of O, to omegas of O. Okay. Below omegas of O, we assume that your gain is equal to 0 dB. Your gain is equal to 0 dB or 1, basically. And then above omegas of O, your gain is increasing by 20 dB per decade. 20 dB per decade. Now, basta't ano, no? Ito numerator, obvious naman na habang lumalaki yung omega, lumalaki yung magnitude ng gain, no? So that's your hint that this should be going up because it is in the numerator. Okay, and then what will your angle look like? The angle of this particular term. The blue curve is the actual curve of the angle. At small values of omega, your angle is equal to 0. At large values of omega, this term will be very much greater than this term. It becomes almost purely imaginary. And we know that when you have a purely imaginary term, your angle is 90 degrees. Pag tinignan nyo sa sa complex plane, no, pag purely imaginary, that means 90 degrees siya. So you start at 0, okay, you end at 90 degrees for large frequencies. From 0.1 omegas of O to 10 omegas of O, your angle is increasing. We approximate it as increasing by 45 degrees per decade. So ito yung phase response. Now, if this happened to be negative, gaya nito, ito mag-flip. Okay? If this happened to be negative, then at large values of omega, ang natitira is negative j omega over omegas O. No? This one becomes negligible. What is negative j? It's an angle that is minus 90 degrees. So this will flip. It starts at 0, then it goes down to negative 90. So ito yung nagiging itsura. That is for your 0 term. Now what about for your pole term? So this is the standard form for your pole term. The 1 plus j omega over omega of O is in the denominator. It's obvious that as omega increases, this quantity is going to decrease. Kasi nasa denominator yung omega, no? So habang lumalaki yung omega, obvious na babagsak yung magnitude natin. So we start at 0 dB. Okay? And then in our 3 dB frequency, we start going down, we start rolling down. Ang roll down ngayon natin is negative 20 dB per decade. 20 dB per decade. I think the last meeting I derived that for you, no? Bakit nagiging 20? Because of this squared, no? Actually, it's supposed to be 10 log, and then because of the squared, nagiging 20. And then yung phase plot natin, okay? You start at 0, you end at 90 degrees. Note that for large values of omega, okay, this dominates over this. So ito yung nangingibabaw. And then if you put j on top, nagiging negative j. Kaya nagiging negative imaginary. So that's minus 90 degrees. Okay? And then you have the same roll down, ano? From 0.1 omega O to 10 omega O, you're going down by negative 45 degrees per decade. Now, if you have a purely imaginary 0 term, kagaya nito, then all you have is a line intersecting omegas of O with a slope 20 dB per decade. And then your angle is just 90 degrees. And when you have a purely imaginary pole term, it's opposite, no? It's a line that is decreasing by 20 dB per decade. Obvious naman, ano? Habang lumalaki yung omega, lumiliit yung magnitude nito, because omega is in the denominator. So it's a line going down by 20 dB per decade, and then your angle is constant at negative 90 degrees. Okay? And then I gave an example, no? Now what I want to do, just so that you get exercised in this, I'm going to give you the seat work to work on. No? And then what I want you to do is I want you to draw the body plot or the both the magnitude plot and the phase plot of your body plot. No? Once you've done it, show it to me. Let's sorry. Let's take about let's say 15 minutes to do this, no? So asan ba yung ginawa ko? Okay. Okay. So let's say this is your function. This is 10 to the 6. No? Okay. Ace of S is 10 to the 6 multiplied by S minus 10, all divided by S squared plus 1,100 S plus 10 to the 5. So, yeah, I'll give you about 10 minutes kaya. Let's see, no? Let's not exceed 15 minutes kasi wala na tayong pwedeng pag-usapan kung masyado tayong tumagal dito. No? And then we'll do it together. So the first challenge here is to put it in the form that will make it easy for you to identify the poles and zeros in the J omega domain, the pole frequencies and the zero frequencies. Yeah, I'm glad to see people are making progress now. I think in general, you know the approach, no? So maybe we can cut that. Let's just do it together para ma-synchronize tayong dalawa, no? So what's the first thing you should do? First thing you should do is you should put it in the standard format where you see all of the poles and all of the zeros, no? So so what is this? This is equal. This is equal to 10 to the 6, okay? S minus 10 over, you can factor out the bottom. So this is S minus 100, and then S minus 1000. Diba? Okay. Now, we want to determine the frequency response. So to determine the frequency response, you replace S with j omega. No? So for frequency response, you evaluate A of S at S equal to j omega. So what do we get? No, we get A of j omega. Okay, this is now equal to 10 to the 6. Then you have j omega minus 10. Okay. Then here you have j omega minus 100. And then you have j omega minus 1000. Sorry. Bakit? Sorry. Ba't naging minus yun, no? Hindi nyo ako kinorekt. Yes? Yeah. Okay. So j omega minus j. Okay, but remember, yung kapartner nung j omega, dapat, it should be of the form, no? Ano yung form na hinahabol natin? Something like this, di ba? Something like this, or something like this. Other it should be 1 plus j omega over something. No? Okay. So how do we do that? So dito, 10 to the 6. Then what I'm going to do is I'll factor out negative 10 sa numerator. No, I'll factor out minus 10. Okay. And then what I will have now is 1 minus j omega over 10. Sorry, 1 plus j omega over, no, sorry, 1 minus, sorry. Okay, 1 minus j omega over 10. Tama? Check on me, ah. Okay. Dun sa denominator, dun sa first term, I factor out the 100. Okay. And then I have 1 plus j omega over 100. Okay. And then dun sa last term, I factor out the 1000. And then I have 1 plus j omega over 1000. Right? So what am I going to end up with? No? I'm going to end up with, well, 10 to the 6 times negative 10, that's 10 to the 7. Right? Negative 10 to the 7 divided by 10 to the 5, or 10 squared, or negative 10 squared, no? So negative 100. Tama? Okay, negative 100, no? Because I have 10 here times 10 to the 6, that's 10 to the 7 negative divided by 100, 10 to the 5 divided by 1,000, 100 na lang natitira. That's why I was saying masyado malaki yung 10 to the 6 mo, no? Okay. And then I have now 1 minus j omega over 10. Okay. 1 plus j omega over 100. And then 1 plus j omega over 1,000. Okay, so how do we get the log plot, the magnitude plot, no? So the magnitude plot, that's 20 log of the magnitude of 8 of j omega 20 log of the magnitude of j omega, that is equal to the 20 log, okay, of the magnitude of minus 100. The magnitude of minus 100, or the absolute value of minus 100, no? Plus 20 log of basically the magnitude of 1 minus j omega over 10, okay, plus 20 log of the magnitude of 1 over 1 plus j omega over 100, plus 20 log magnitude of 1 over 1 plus j omega over 1000. Okay, magnitude, no? Magnitude. Right? Okay, the reason why we can do that is because these are logarithms, no? When you have products, if you get the logarithm, you're just adding the logarithms. So ano yung 20 log of 20 log of the magnitude of 100 minus 100? Of course, the magnitude of minus 100 is 100. The log of 100 is 2. So 20 times the log of 2, that's equal to 40 dB. No? So yung first plot ko, that's 20 log of the magnitude of minus 100 is equal to 40 dB. 40 dB. We always deal with magnitudes, no? Dun sa magnitude plot. So meron akong plot na ganyan na 40 dB. Okay? This is the log of omega, no? Yun yung una. Yung pangalawa, 20 log of 1 minus j omega over 10. What is this? This is a zero term. So 20 log of the magnitude of 1 minus j omega over 10. Okay. What is this? This is a zero term. No? The magnitude is increasing as omega increases. So that's your hint that dapat paakyat siya. So you start at 0. You start at 0 dB. Saan siya umpisa mag-aakyat? At 10, right? So this will go up at 10. So this is 10, omega equal to 10. That's omega. And this is what? 20 dB per decade. Okay. Okay, the next term is 20 log of the magnitude of 1 over 1 plus ano? Yeah. J omega over 100. No? So this is now a pole term. Ano nangyari sa pole term? Habang lumalaki yung omega, lumiliit yung magnitude natin because your omega is the denominator. So if you get the plot of this, okay, this will start at 0 dB. And where will it start to drop off? At 100. 100. Okay. And finally, the last term, ganito din yung itsura. Okay, hindi ko na isusulat yung formula. Nakatamad. No. Where will it start dropping off? Sa 1,000. Okay, so this is 40 dB. Okay, so what do? I just add all the three together. Okay? So when I add all the three, what will come out? Okay, so this is my dB scale. This is the log of omega. I have 10, 100, 1,000. Okay, from 0 to 10, So andito, no, 10, 100, 1,000. From 0 to 10, I have 40 dB. No? So let's say that's 20, this is 40. So this is 40 dB. So hanggang 10, I have 40 dB. Okay. Ano mangyayari at 10? At 10, madadagdag, may madadagdag na 20 dB per decade. Right? So I will go up this way. Mali pala, no? Masyadong mataas yung 40 dB ko, no? But now this point will be 60 dB. Right? This is now going to be 60 dB. That is by the time I reach 100. But what happens when I reach 100? I reach 100, I have now two components that are working. One is pulling the graph 20 dB up, but the other is pulling the graph 20 dB down. Right? So this will be 0. Okay? That will be 0. And then pagdating natin sa 1,000, I now have something pulling it down by 20 dB per decade. Right? So this will go down this way. Sorry. This will go down this way. So at what frequency will the gain be equal to 0 dB or 1? If that's my next question. So at 10,000, it will be 40 dB. At 100,000, it will be 20 dB. And then at 1 million, it will be 0. Right? So if I extend this all the way here, no, ano yung magiging frequency na yan? That should be no? This would be 10,000. Sorry, this would be 10,000, and then 100,000, and then 1 million. No? So this is 10 to the 6. 10 to the 6. Okay? So now you have an idea of your frequency response. You start with a gain of 40, tapos aakyat siya at between 10 and 100, and then it tapers off, and then it starts going down. Okay. What about the angle? Okay, the angle is, there's one thing that's going to be a little bit tricky in the angle. Okay. So first thing is this, no? So we're looking at the angle. Angle of base of j omega. So what you're going to do is you're going to get the angle of this term, the angle of this term, plus the angle of this term, plus the angle of the pole term, plus the angle of the pole term here. No? What is the angle of minus 100? What is the angle of minus 100? Anyone? I heard something. Ano yun? Negative. Anong angle ng minus 100? Asan yung minus 100 dun sa plane natin? It's on the left side. So what is that angle? It's 180 degrees. Right? 180 degrees. Remember, lagi nating sinasabi niyan na when you're 180 degrees out of phase, nagiging negative lang yung value natin, ano? So the angle of minus 100 is actually 180 degrees. Actually, you can use either negative 180 or positive 180. No? Positive 180 if you're going clockwise, negative 180 if you're going counterclockwise. Now, the thing is this, no? You use whatever that will result in angles that are positive as much as possible. No? Okay, what is the angle of this? No? Sorry, ito pala. What is the angle of this? No? that is a zero term, pero negative siya. So it's the flip. It's the flip, di ba? Di ba? Pag positive to, let's say this is 1 plus j omega over 10. If that's 1 plus j omega over 10, you're starting at an angle 0, you're ending up at an angle 90 degrees. Pero kung 1 minus j omega over 10, you're starting at an angle 0, you're ending at an angle negative 90 degrees. So ang magiging itsura ng angle nito, no? So this is plus the angle of 1 minus j omega over 10, no? Ano magiging itsura ng angle na yan? Okay, you're starting at 0, you're going to end at minus 90. Okay, so let's say this is minus 90. So that's going to be this way. Kailan siya mag-uumpisang mag-break? At what frequency will it start to break? 10? Is it 10? 1, that's right, 1. And then this is now 10, and this is 100. Okay? Ito naman, no? Plus the angle of no, we're here, no? 1 over 1 plus j omega over 100. Okay. This is a pole term. This is a pole term. So you start again at 0 degrees. Okay. Now take note, no? Yung j natin is nasa denominator, no? I'm just telling you how to remember the shape, no? Your j is in the denominator. When this term becomes very large, nagiging negligible to, then you have 1 over j, no? Which is negative j, right? When you have 1 over j, that's negative j. So what angle do you end up? You end up also in negative 90 degrees. That's also where you end up, negative 90 degrees. So actually, yung shape niya magiging parang ganito. It's going to be almost exactly the same shape, no? Except that the breakpoints are different. So where will we start? You start at 10, okay? And then you have 100, and then you have 1,000. So parang ganyan siya. Okay? This is minus 90 also. And then finally, the last term is just start at 100. No. The last term is you start at 100. This is 1,000, and then 10,000. So ganun din, no? So this is minus 90 degrees. So now you just add up all of those. Okay? So kaya na nyo yan. You just have to add up all of this, no? So from 0 to 1, obviously it's 0, no? From 1 to 10, you just have negative 45 degrees per decade from 1 to 10. What about from 10 to 100? From 10 to 100, you have two components now, no? You have negative 45 degrees per decade, nandun pa rin yun, pero madadagdagan ng another negative 45 degrees per decade, kaya magiging mas steep siya pababa, no? And then from 100 to 1,000, well, hanggang, teka, no? Actually, remember, ito nagiging 0, no? Ito nagiging 0. So from 10 to 100, you're going to get negative 90 degrees per, you're going to get negative 45, you're going to get negative 90 degrees per decade. Pero pagdating ng 100, this is already steady at minus 90. So this is going to be flat at minus 90, tapos madadagdagan ka ng negative 45 again. Anyway, it's something, I'm sure you can figure this out yourself, no? Okay? So, are we clear on that? Okay, so yun, no? I just wanted to introduce an exercise para makita lang nyo how how you apply these principles which we took up last time. It took longer than I wanted to, unfortunately. Okay, so let's continue with the rest of the let's continue with the next subject matter. Okay, so this is supposedly what I was going to cover up now, except that half the time already is gone. No? So this is what I wanted to cover today. First, we'll cover gain bandwidth product, then transistor capacitances, then the refined small signal model of the transistor, then transistor frequency, transition frequency rather. No, I prepared some. I would have done this lecture blackboard style, no, writing everything down. Pero dahil nga kulang tayo ng oras, I already prepared some slides, and these are patterned after or almost the same as the slides, official slides sa UVLE. No, maybe I just omitted certain things. Like I said, no, my intention is not to repeat what is being given to you already in UVLE, but rather just to emphasize the things that I think are important. Okay, so first let's discuss gain bandwidth product. So let's consider a single pole amplifier. So single pole amplifier, we already said that will have a transfer function of this format, no, A of j omega AO1 over 1 plus j omega over omega p, where omega p is your pole frequency. And if you take a look at the magnitude plot of this, magnitude plot lang muna tignan natin, no? That's going to have this shape, no? Where this, ano ito? This is negative 20 dB per decade. So, yeah, this consists of two parts. Una yung 20 log of ace of O, and then you add to that the Bode plot of this. No? This starts at 0 dB going down, pero dadagdagan mo ng 20 log of ace of O, kaya parang umaakyat siya. The flat part is this, and then going down minus 20 dB per decade. Okay, we define omegas of mu as the unity gain frequency. We define this as the unity gain frequency. This is the frequency in which the gain goes down to 0 dB. What is 0 dB? What is pag gain is 0 dB, what does that mean? What is A out? What is V out over V in? That's equal to 1. Okay, that's equal to 1. That's why you call it the unity gain frequency. This is the frequency at which the gain is equal to 1. Okay, we know that ace of j omega, the magnitude, okay, what is that? That is equal to ace of O over the magnitude of the denominator. Ano yung magnitude ng denominator natin? That is the square root of 1 plus omega over omega p squared. Okay. Now, what do we want to do? We want to find the value of omega where ace of j omega, the magnitude of ace of j omega is equal to 1. No? So we're saying that at omegas of u, this one is equal to 1. Right? So you have 1 is equal to ace of O all over 1 plus omegas of u over omegas of p squared. Right? Okay, teka lang. Yeah. If omegas of u is very much greater than omegas of p, omegas of u very much greater than omegas of p, itong 1 dito sa baba, magiging negligible. And what we will get is, we're just going to get a's of O is equal to omegas of U over omegas of P, no? Because you're getting the square root of S square. So nawawala yung square root, nawawala din yung square, no? Or omegas of U is equal to a's of O multiplied by omega P. Now, itong a's of O multiplied by omega P, we have a term for that, no? A's of O, omega P, you call this the bandwidth of the system. So ito yung bandwidth. Okay? That's a's of O multiplied by omega P. Okay, let's call now the, sorry about that. No. Ang bandwidth is omega P, sorry, no? Omega P is called the bandwidth. Ito, omega P, this is called the bandwidth of the system. In other words, if this is a, kaya tinawag yan na bandwidth, ano? This is actually the frequency plot of a low-pass filter. So it passes the low frequencies, it eliminates the high frequencies. So if you consider this to be a low-pass filter, what is the bandwidth? The bandwidth is the range of frequencies that it will pass, supposedly that it will pass unattenuated. And therefore, that is omegas of P, no? From 0 to omegas of P, those are the range of frequencies that it will pass unattenuated, kaya tinatawag natin yung bandwidth ng system, no? Now, what I wanted was itong a's of O multiplied by omegas of P. We have a special term for this, no? We call this the gain bandwidth product, no? Or GBP, gain bandwidth product. And that is a parameter of a component, for example, of a transistor or even of an op-amp. Pag tinignan nyo yung data sheet ng transistor or data sheet ng op-amp, makikita nyo yan, ano? Gain bandwidth product. Okay, what good is it to know the gain bandwidth product, no? Using the gain bandwidth product for a given frequency omegas of X, I can approximate the value of my gain. Okay. I can approximate the value of my gain. Okay? Because, for example, no? Ito. Okay? At omegas of X, no, let's go back to ano. Let me go back to okay. Let me go back to this, no? A's of J omega is equal to A's of O over square root of 1 plus omega over omegas of P squared, no? At omega equal to omega U or omega X, no? Let's say omega equal to omega X. Let's assume omega X is very much, omega X over omega P is very much greater than 1. Okay. Then at omega equal to omegas of x, no, my gain A, no, at omega equal to omegas of x is just going to be a sub O all over what is this? Omega x over omega p. Right? How is this? Yeah. We call this a sub x. No? In other words, a sub x omega x is going to be equal to a sub O omega p. Right? But this is my gain bandwidth product. That is my gain bandwidth product. So what does this mean? You know? For any frequency above omegas of p, if I want to have an idea what the gain is going to be, I just divide my gain bandwidth product by that particular frequency. And I'm going to have a good idea of what the gain is going to be. No? In other words, a sub x is just my gain bandwidth product over omegas of x. Okay? So yun yung ganda nung knowing the unity gain frequency. No? Because if you know the unity gain frequency, then you have an idea of what your gain bandwidth product is. And if you know your gain bandwidth product, then you can approximate your gain for any particular frequency. Okay, there are mahaba-haba pa pala to, no? There are different considerations when you have now a two-pole system. So let's say I have a two-pole system. So I have two poles, omega p1 and omega p2. What is going to be my omegas of mu, no? No? So this is my unity gain frequency. Okay. So again, I can get a of j omega that is equal to a of O. The magnitude, now I have two terms underneath. The magnitude of my first pole is going to be 1 plus omega over omega p1 squared. Okay, and then the magnitude of my second pole is going to be 1 plus omega over omega p2 squared. Okay, let's assume omega of mu is somewhere between omega p1 and omega p2. So, no? Let's assume that. In other words, pag dinrawing ko yung I drew it here, no? I already drew it here. Para hindi magulo. Okay. So let's assume that omegas of mu is between omega p1 and omega p2. In other words, pag dinrawing ko yung magnitude response nito, yung body plot ng magnitude nito, okay, you're going to start in a of O, di ba? And then at omega p1, yeah, you're going to start at a of O, and then at omega p1, you're going to roll down by 20 dB per decade. And then at omega p2, you're going to roll down again by 20 dB per decade, no? And then let's assume that omega of mu is somewhere between omega p1 and omega p2. So anong lumalabas na unity gain frequency? So sinulat ko na dito kanina. My PowerPoint just hung. I'll have to restart my PowerPoint, sorry. Okay, A's of j omega is equal to 1 all over 1 plus omega over omega p1 squared, then 1 plus omega over omega p2 squared. Okay, so if muse of mu is greater than omega p1 is less than omega p2, what are my approximations going to be? So at okay, at that, okay, at omega equal to omega of mu, ano mangyayari? Because this is less than this, because this is less than this one, okay, will be small with respect to 1, right? So this will become negligible. But because this is greater than this term will be great with respect to 1, and so ito yung magiging negligible. Right? So anong lalabas, well, this is supposed to be equal to 1 now, because that's your unity gain frequency. So this is going to be 1 over square root of, ang matitira na lang is omega over omega p1 squared. Yun na lang matitira sa taas. So this is omega mu. Sorry, nawala yung a's of O. Okay. And you're going to get omega mu is the same, a's of O omega p1. You're going to get the same thing. So pareho yung result, from the previous. Previously, we got the same result, So kung dalawang pole, basta't yung transition frequency is between the two, then you can approximate the value of omega mu to be based on only omega p1. Okay, ngayon, what if omega mu is greater than omega p2? So ngayon, pag tinignan natin yung magnitude plot natin, it will roll off minus 20 dB and then minus 40 dB until it hits omegas of mu here. I won't go through the math anymore, but in this case, ang magiging negligible dito sa denominator is yung 1. Parehong 1 yung magiging negligible. And if you compute for omegas of mu, this is going to come out to this, a's of 0, omega p1, omega p2. Okay. So I leave it up to you to figure this out, Pero madali lang, Ang magiging negligible itong 1 dito at saka itong 1 dito. Okay. So again, what is the use of omegas of mu? It's a way of you determining approximately what the gain of your system is going to be at any given frequency. Because omegas of mu is equal to your gain bandwidth product. Okay, let's move on. So frequency dependence of a circuit. Now, frequency dependence is because of the presence of inductors and capacitors. Pag wala kang inductor, wala kang capacitor, pag puro resistor, your circuit will behave in the same manner for all frequencies, for all possible frequencies. Pero the minute you put an inductor or the minute you put a capacitor, things change. Bakit? Because the impedance of your capacitor is what? 1 over j omega c. Andun yung omega. No? Lumiliit yung impedance habang lumalaki yung omega. And the impedance of your inductor is omega L, j omega L, no? Lumalaki yung impedance habang lumalaki yung frequency. Okay, you have external capacitors and inductors, and you also have parasitic capacitors and inductors. When you say external, yon linalagay talaga yon. Naglalagay kayo ng capacitor, naglalagay kayo ng inductor dun sa circuito nyo, no? But when you have parasitics, these are things that are already inside your components. Hindi mo matatanggal to. And most of the time, these are unwanted. Hindi natin gusto, pero nandun. No? For example, I'll give you an example, PN junction, okay? There is a capacitance between the anode and the cathode, which we don't want, but unfortunately it's there. And I'm going to explain that more in detail later on. Okay. Now, when we implement frequency-dependent circuits, most of the time we use capacitors rather than inductors. It's more common to use capacitors, no? Because capacitors are more readily available. They are smaller in size. No? Yung mga inductors mo, these are windings. Usually they are larger. No? But sometimes you cannot avoid using inductors, especially when you're implementing what we call tuned circuits. Because for you to implement a tuned circuit, you have to have both positive and negative reactance. No? I'm sure you studied resonance. You studied resonance, so you know that you cannot have a resonant circuit unless you have both inductors and capacitors. No? Those are your tuned circuits. And you see this a lot in communications. Pag gumagawa kayo ng mga, for example, transmitters and the like. No? Okay. Parasitic capacitances are more prevalent than parasitic inductances in amplifier circuits. In other words, especially in integrated circuits, usually yung mga parasitics mo sa ICs, these are capacitances. No? Because the inductance of an integrated circuit trace, papasok lang yung inductance ng trace na yon at really high frequencies already. Mataas na frequency. So usually we can neglect parasitic inductances in your integrated circuits. Okay, so let's talk about transistor parasitic capacitances. So BJTs, unahin natin yung BJTs. Yung bipolar junction transistors, your capacitances are associated with your PN junctions. So how many junctions do we have in a BJT? We have two junctions. You have your base emitter junction and you have your base collector junction. So between your base and emitter, there's going to be a parasitic capacitance. We can lump this into a single capacitance. No? And then between your base and collector, there's also going to be a parasitic capacitance. So we're talking about capacitances associated with PN junctions. When you're talking about PN junction capacitances, there are two types. You have what you call your junction capacitance, and this is because of the depletion region. This is because of the existence of charge in your depletion region. And then the second type is what we call the diffusion capacitance, and this is due to the injection of minority carriers into the base. So let me just describe each one in turn. Junction capacitance. This is due to the existence of charge in the depletion region. If you recall, so babalik tayo sa Di maiiwasan, no? Babalik sa module 1. Okay, you have a p-n junction. So let's say this is your p side and this is your n side. Ano? Anong nangyayari when you put the junction together? No? When you put the junction together, you have holes here. No? So these are holes that go toward the n, no? Holes. And then you have electrons here that go toward the p. So electrons. No? Okay, yung inaalisan ng electrons nagiging positively charged. Yung inaalisan ng holes nagiging negatively charged. Remember that holes act positive charges. When your hole goes somewhere else, yung iniiwanan niyang atom in effect becomes negatively charged pag nawala yung hole, no? And nagkakaroon ka ng depletion region, no? So we end up having what you call a depletion region. So this is now your depletion region. Okay. Where this now becomes positively charged. And then this becomes, negatively charged. Kung umalis yung hole, which is a positive charge, this becomes negatively charged. And then this now becomes positively charged. That's what's going to happen. So you have a charge distribution in your depletion region, negative sa kaliwa, positive sa kanan. Okay. And there's a certain capacitance that is associated with that, no? Because of this, because of this charge, no? Alam nyo that nagkakaroon ng built-in potential, di ba? Because of that charge. Kasi nagkakaroon ka ngayon ng electric field from your plus to minus, and therefore nagkakaroon ka ng built-in potential dBi. And the capacitance associated with that, this is proportional to Q over V. No? C is actually Q over V. No? Yung under DC condition, C is equal to Q over V. No? If your conditions are changing, it's a partial of Q over partial of V. No? Where Q is ito, no? The charge associated here. Okay, without going through any derivations, okay, this is the formula for junction capacitance. No? So note that, okay, ito yung formula, no, for junction capacitance. Okay, so Cj is Cjo over the square root of 1 minus V sub O over Vbi. So this is your junction capacitance, Cj. This is the capacitance across the unbiased junction. V sub O is the voltage across the junction, and Vbi is the built-in potential of the junction. So note that Cj is both nonlinear. This is a nonlinear quantity, and is also a bias-dependent quantity. It depends on the bias that is placed across your junction. And Cj is predominant in reverse bias junctions because when your junction is reverse biased, that is when your built-in potential is the largest, and that is when your depletion region is also the widest. Now we have two junctions. You have your base emitter junction and you have your collector base junction. Okay, so you have CJE. This is the junction capacitance at your emitters, that CJEO, the unbiased junction capacitance. Instead of VO, we have VBE. And let's assume that the built-in potential for the emitter-based junction is VJBE. Yun yung built-in potential. Okay, yung collector base naman, CJC, we call that CJC. We also call that Cs of mu. I'm going to explain later why we call it Cs of mu. No? This is now Cs of mu O, the unbiased capacitance. Now, why did this become positive? This is supposed to be VBC. No? This is from base to emitter. Okay, this is from base to emitter, because that is that is what will forward bias. That is what will forward bias the junction. No? So this is supposed to be VBC, but since your collector to base in a transistor is always reverse or almost always reverse biased, di ba sa active mode, when we're using your BJT in active mode, your collector to base is normally reverse biased. So ginawa ating VCB to, and then we made this positive. Otherwise, it's the same formula. If you take a look at typical values, this is typically much larger than this, in the order of 10 times, larger. Yung emitter capacitance is larger than your collector. Your emitter to base capacitance is larger than the collector to base capacitance. So typically this is in the tens of femtofarads, and this would be in the single digit femtofarads. Femtofarad is how much? 10 to the minus 15. 10 to the minus 15. Femto 15, ano yung 12? Pico, that's right, no? And then 9 is nano, then 6 is, minus 6 is micro. Okay, so yun yung first type, no? First type is your junction capacitance. Meron tayong second type, which is your diffusion capacitance. Diffusion capacitance. So this is due to the injection of minority carriers into the quasi-neutral area of the PN junction. Quasi-neutral, you remember that term from module 1? Pag sinabi natin quasi-neutral area, that is the area of your diode that is not under the influence of an electric field, basically. Kasi yung electric field natin usually nako-concentrate dun sa junction area. Paglabas mo sa junction area, usually wala nang electric field doon, no? Anyway, what does this look like? Ano? If we let's assume an NPN, no? Assume an NPN. Okay, so we have two junctions. So this is our emitter, this is our base, this is our collector. Okay, we have an emitter to base junction. So meron tayong depletion region between my emitter to base. So these are my junctions, no? Junction. I have a depletion region between my emitter and base. And the depletion region in my emitter is usually going to be, the depletion region in my base is usually going to be smaller the emitter is high, the base is it's going to be larger, no? Sorry. It's going to be larger. So ito yung depletion region ko. The depletion region in my base is going to be larger than the depletion region in my emitter because my emitter is more highly doped, much more highly doped than the base. No? Remember yung condition natin sa BJT, the base should be very lightly doped. No? or it will take more space, more space to deplete, to match the electrons, no? Electrons coming from the emitter, maraming space dun sa base para yung mga holes coming from that area will match the electrons coming from the emitter. No? Now, what happens when I forward bias the emitter base junction? No? So this is NPN. So I'm going to get electrons injected to the right, holes injected to the left. But the electrons injected to the right will be much more than the holes injected to the left because my base is very, very likely doped. No? If I take a look at the injection, siguro ito lang yung injected holes, no? And then siguro ito yung injected electrons ko. No? The profile of the electron concentration is going to be exponential. Okay. So this is going to be my hole injection, holes injected. And then this is going to be the electrons injected. No? And because of this profile, what do we get? We get diffusion. Diba? Because diffusion is caused by a non-uniform concentration. Dahil bumabagsak yung concentration natin, nagkakaroon tayo ng diffusion of electrons to the right. So yung electrons natin ngayon, because of this, pupunta dito sa kanan. Unfortunately, no, it will soon hit the depletion region from my collector to my base. No? So this is my other depletion region. No? So hindi siya magkakaroon ng pagkakataon na mag-recombine dito kasi habang gumagalaw pa lang siya, papasok na siya rito sa depletion region na to, mahihigop na siya ng collector. So that's what's happening. No? Anyway, what I wanted to point out is these are injected electrons. So this corresponds to a certain charge, no? Which is negative. So meron akong charge that accumulates here. And whenever you have accumulation of charge, then there's a capacitance effect when there is accumulation of charge. What is the amount of this charge? No? The amount of that charge, let's call it Q minus because it's a negative charge. I'm assuming this is an NPN. This is equal to your collector current multiplied by taus of F. I wonder if I have that here. Yeah, andito pala siya. No? Q minus is I sub C multiplied by taus of F. Collector current multiplied by taus of F. Let me clean this up a little bit so you can see it. Okay. Where taus of F is what we call the base transit time. This is the average time for a charge carrier to traverse the base region. Capacitance hang na naman. Okay, I'll just write it down. Ano? Capacitance, let me call this C sub B. This is my base capacitance. Again, you can compute this as the partial of Q, in this case Q minus, with respect to VBE. But I said that Q minus is equal to IC times TF. No? So this is T sub F, my base transit time, the partial of I sub C with respect to VBE. Do you recognize this? The partial of IC with respect to VBE. That's equal to GM. In other words, your base capacitance is just your base transit time multiplied by your transconductance. Okay, what? Oh, finally, lumabas siya. Okay? And typically, this will be in the hundreds of femtofarads. So typically, it will be 10 times your junction capacitance, your base to emitter junction capacitance. Okay, so I now have this modified small signal model of my BJT. Okay, this is C sub mu and this is C sub pi. What is C sub pi? C sub pi is my input capacitance that is two components. That is my base capacitance, which is due to diffusion. This is diffusion capacitance, plus CJE, which is due to the depletion region. So there are two components here, no? I can lump these two capacitances into one, and that is C sub pi. And I already gave you the formula for your depletion capacitance or junction capacitance, and then the base capacitance. And then the other capacitance is C sub mu. We call this your Miller capacitance. It's called a Miller capacitance. A Miller capacitance is associated with a capacitance that connects your output to your input. In this particular case, my output, no, this is my output, this is my input, and the capacitor bridges the two. Yun ang tinatawag nating Miller capacitance. And I already gave you the formula for your Miller capacitance. Now, these formulas, don't let that intimidate you. You're not going to be using that in your exams or in your problems. No, it's just presented there so that you know that there's a basis for the values. Usually binibigay yung values nito. No, these are parameters of your transistor, and these values will be given to you when you solve problems. Okay, so I'm going to stop here. I only covered probably 1/4 of what I wanted to cover. But yun nga, no, like I said, no, I don't want this to go too fast because there's a lot of material to cover. So kung hindi tayo matatapos, we'll just continue after next week. So that's all for now, no? Okay, thank you.